Welcome, I'm Satya. Molecular orbital theory. So the outline of the presentation gives us explanation regarding introduction, types of molecular orbitals, formation of molecular orbitals, key features of the molecular orbital theory, and characteristics of bonding and anti-bonding molecular orbitals, and salient features of molecular orbital theory, rules for filling of orbitals, with example oxygen molecule. In introduction, the molecular orbital theory is a theory on chemical bonding developed at the beginning of the 20th century by F. van Hund and R. S. Mulliken to describe the structure and properties of different molecules. The valence bond theory failed to adequately explain how certain molecules contain two or more equivalent bonds whose bond orders lie between that of a single bond and that of double bond, such as the bonds in resonance stabilized molecules. This is where the molecular orbital theory proved to be more powerful than the valence bond theory, since the orbitals described by the molecular orbital theory reflect the geometries of the molecules to which it is applied. In linear combination of atomic orbitals, molecular orbitals are generally be expressed through linear combination of atomic orbitals. These LCAOs are useful in the estimation of formation of these orbitals in the bonding between the atoms that make up a molecule. The Schrödinger equation used to describe the electron behavior for molecular orbitals can be written in a method similar to that for atomic orbitals. It is an approximate method for representing molecular orbitals. It's more of a superimposition method where constructive interference of two atomic wave functions produces a bonding molecular orbital, whereas destructive interference produces a non-bonding molecular orbital. Types of molecular orbitals. According to the molecular orbital theory, there exist three primary types of molecular orbitals that are formed from the linear combination of atomic orbitals. Bonding orbitals. The bonding orbital is used in molecular orbital theory to describe the attractive interactions between the atomic orbitals of two or more atoms in a molecule. Anti-bonding molecular orbitals. The electron density is concentrated behind the nuclei of the two bonding atoms in anti-bonding molecular orbitals. This results in the nuclei of the two atoms being pulled away from each other. These kinds of orbitals weaken the bond between two atoms. Non-bonding molecular orbitals. In the case of non-bonding molecular orbitals, due to a complete lack of symmetry in the capability of two bonding atomic orbitals, the molecular orbitals formed have no negative or no positive interactions with each other. These type of orbitals do not affect the bond between the two atoms. Formation of molecular orbitals. An atomic orbital is an electron wave. The waves of the two atomic orbitals may be in phase or out of phase. Suppose psi A and psi B represent the amplitude of the electron wave of the atomic orbitals of two atoms A and B. In case 1, when the two waves are in the phase as they add up, and amplitude of the wave is psi A plus psi B. When the two waves are out of phase, the waves are subtracted from each other so that amplitude of the new wave is psi A minus psi B. Key features of the molecular orbital theory. The total number of molecular orbitals formed will always be equal to the total number of atomic orbitals offered by the bonding species. There exist different types of molecular orbitals: bonding molecular orbitals, anti-bonding molecular orbitals, and non-bonding molecular orbitals. Of these, anti-bonding molecular orbitals will always have higher energy than the parent orbitals, whereas bonding molecular orbitals will always have lower energy than the parent orbitals. The electrons are filled into molecular orbitals in the increasing order of the orbital energy, from the orbital with the lowest energy to the orbital with the highest energy. The most effective combinations of the atomic orbitals occur when the combining atomic orbitals have similar energies. Characteristics of bonding molecular orbitals. The probability of finding the electron in the internuclear region of the bonding molecular orbital is greater than that of combining atomic orbitals. The electrons present in the bonding molecular orbital result in the attraction between the two atoms. The bonding molecular orbital has lower energy as a result of attraction and hence has greater stability than that of the combining atomic orbitals. They are formed by the additive effect of the atomic orbitals, so that the amplitude of the new wave is given by psi a plus psi b. They are represented by sigma, pi and delta. The probability of finding the electron in the internuclear region decreases in the anti-bonding molecular orbitals. The electrons present in the anti-bonding molecular orbital result in the repulsion between the two atoms. The anti-bonding molecular orbitals have higher energy because of the repulsive forces and lower stability. They are formed by the subtractive effect of the atomic orbitals. The amplitude of the new wave is given by psi a minus psi b. They are represented by sigma star, pi star and delta star. The lowering of the energy of the bonding molecular orbital to the combining atomic orbital is called stabilization energy. And similarly, an increase in energy of the anti-bonding molecular orbitals is called destabilization energy. The salient features of molecular orbital theory. The atomic orbitals overlap to form new orbitals called molecular orbitals. When two atomic orbitals overlap, they lose their identity and form new orbitals called molecular orbitals. The orbitals in the molecules are filled in the new energy states called the molecular orbitals, similar to the electrons in an atom being filled in an energy state called atomic orbitals. The probability of finding the electronic distribution in a molecule around its group of nuclei is given by the molecular orbital. The two combining atomic orbitals should possess energies of comparable value and similar orientation. For example, 1s can combine with 1s and not with the 2s. The number of molecular orbitals formed is equal to the number of atomic orbitals combined. The shape of molecular orbitals formed depends upon the shape of combining atomic orbitals. According to molecular orbital theory, the filling of orbitals takes place according to the rules of Bose principle. Molecular orbitals are filled in the increasing order of the energy levels. Pauli's exclusion principle. In an atom or a molecule, no two electrons can have the same set of 4 quantum numbers. According to the Hund's rule, pairing of electrons does not take place until all the atomic or molecular orbitals are singly occupied. For example, oxygen molecule. So, oxygen molecule belongs to the family of diatomic molecules, which consist of two oxygen atoms bonded to each other by a covalent bond. Bond order: number of electrons in a bonding molecular orbital minus number of electrons in anti-bonding molecular orbitals divided by 2. So if we calculate the bond order by taking the outermost electronic configuration, we are filling the electrons in the 2s and 2p. So here the two unpaired electrons are present. Due to the presence of unpaired electrons, the oxygen molecule should be paramagnetic. The electronic configuration of this is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2p2y, pi star 2py and pi star 2p x1 and y1. Thank you.